Welcome everybody, this is Noor and today I'm going to present emotional body gesture recognition. So in this presentation I will be focusing on the survey on emotional body gesture recognition. So I will not explain all of it because they have proposed a lot of approaches, but I will choose like the most important approaches in this survey to recognize emotion through body gestures. So we often use like non-verbal communication. Sometimes we use like facial expressions, like here she is sad, here she is happy, for example. And sometimes we use like body gestures or postures, like here she is shocked. Through this non-verbal communication, we can share feelings, thoughts, and also emotions. These movement and expressions, we always call it like body language. So why did I choose this topic specifically? Because while I'm searching, I found that we can easily notice emotions through facial expressions. But on the other hand, noticing emotions become more challenging when it comes to the body. Like here, some emotions we can see can be expressed through different poses and different ways. These emotions can be presented differently according to the culture and the gender. So we have like 6 basic emotions that seem to be universal and common. These 6 emotions are anger, disgust, fear, happiness, sadness, and surprise. These 6 emotions follow general movement protocols. Like if someone afraid, his elbow will be dragged inward, as we can see here. If someone is sad, then he will bend their head and drop their bodies. Before I discuss how to recognize emotion from body gesture, I would like to discuss the input modeling and the output modeling. The input modeling, which is the human body posture or motion, the output modeling, which is the emotion labels. Let's see. So there are some models that we can use to detect human body. The first one is part-based models. Second one is kinematic models, which I will discuss in a few seconds. The part-based models, from its name, we can get that we can detect body parts independently. As we can see here in the picture, the head and the hands are detected independently. In part-based models, there are various examples. Here I will discuss 2 examples. The first one is pictorial structures, which is a collection of humans' body parts with a connection between certain pairs of these parts, as we can see here in this image. The head is connected to the torso, and then torso with the arms, and so on. So second example is grammar models, which apply 2 rules. The first one is compositional rules, which means that the human body composed of, like, for example, a trunk, limbs, and face. And the face also is composed of eyes, nose, and mouth, and so on. The second rule is deformation rules, and which lead us to a hierarchical deformation. For example, in this picture we can see we have the model, for example, which is the human body, and then there's a list of objects of this human body. For example, we have like the torso, the limbs, and the face, and then here we will deform this list of objects to like here the face, for example, the torso, and so on. And then the face itself is deformed to, like, for example, a list of objects again, which is the nose, the mouth, and the eyes, and so on. So now we have discussed the part-based model. The second one is the kinematic models, which, as we can see here in this image, it's an interconnected joint which are collected with the predefined degrees of freedom similar to the human skeleton. So we have discussed the input models, which were the human poses and human motion, and now we will discuss the output models, which is the emotion labels. And emotions have been described in various ways. It can be described in categorical models, where we classify emotions into a set of classes, and dimensional models, where models emotions can be represented along a set of dimensions like x, y axis, and then we have some representations for these emotions. And the last one is componential models, which is not usually used, and it arranges emotions in hierarchical fashion, as we can see in this image, and each superior layer contains more complex emotions as we go from here to here. And then more complex emotions are a combination of pairs of more basic emotions. So one simple example, we can see that love here is a combination between trust and joy. Okay, to recognize emotions from body gestures, we have to go through some steps as shown here in this pipeline. So first, we will get the input from a camera or a Kinect, and then we will detect the human body, and then we will estimate the body pose, and then with the help of the representation learning by extracting features that can be fed then to a classification model, which then will recognize the emotion. So let's discuss each step. So now, how can we detect humans in images and videos? So there are some common approach that is being used to detect humans in images and videos. The first one is histograms of oriented gradients plus the support vector machines SVM, a classifier. The second one is deformable part models, or we can use deep neural networks like the convolutional neural networks to train our model to detect humans in images and videos. So the first approach I will discuss is HOG plus SVM. So as you can see, I've summarized it in this pipeline, but I would like to explain it on a drawing. So let's say we have an image, and this image I will crop a slide window with a dimension of 64 times 128, and I will calculate HOG plus SVM for this cropped image. And then I will have another slide window with dimensions of 64 times 128, and also I will calculate HOG plus SVM for it, and so on. Then for this cropped image, I will divide it to 8 times 8 cells. So I have 8 times 8, 8 times 8 cells. So I will have 8 grids here, or 8 cells, and I will have 16 cells here. And then I will calculate for each, like in this grid, which is this one, for each point in it, I will calculate the intensity of the pixel intensity. So I have here like x direction and I have y direction around this point, and so the x direction is like this point minus this point, and the y direction is this point minus this point, and I will take their absolutes, which will give me the x direction and y direction. And then I will calculate the grad magnitude. So I have calculated the x direction and y direction to calculate the gradient magnitude, which is the square root of x square plus y square, and then I will get the angles, which is the grad direction, which is the tan inverse of x direction over y direction. So now I have a grad magnitude matrix, and I have a grad direction matrix. So we will find that each grad magnitude, like this part of the matrix, this value, is dependent on this grad direction. And this is what we will apply here. So our angles are from 0 to 180. If we divided it by 9 vectors, we will have here from 0 to 20, we will have here from 20 to 40, and so on till last one is 160 to 180. So let's say we have here, like in this part, we have a value of 20 degree, an angle of 20 degree. Then I will see what is the corresponding value for this in the grad magnitude. Let us say it's 2. Then I will put here the value 2, and so on. And then I will have this, like, for the window, for the image I have. Now this grad has a 9 feature vectors. This grad has a 9 feature vector. I will concatenate each 4 feature vectors together. So I have 36, which is 9 plus 9 plus 9 plus 9, and then another slide window, which is 9 plus 9 plus 9 plus 9, and so on. In that case, I will have 3780 feature vector. Then I will normalize them. So it wouldn't be affected with the change of the light intensity if we applied. The last step is to apply it to an SVM classifier to detect if it's a human or not. So the second approach here is the DPM, which is deformable part models. These deformable part models is consisting of 2 paths. So I will explain it here. It's better than reading. So first of all, we will extract from this image the feature map using HOG, as we have explained on the last slide. Then we will multiply it with the SVM coefficient of the whole body, and we will get the results here. And then in this paper, I have referenced it like in references, you can check it later. So they have divided the body into 6 parts. So we have like the heads, the right part, the left part, this part, and the legs. So here we will use this concept here. So we have like the image, and we will twice the resolution, and then again we will extract the feature maps using HOG also. But then here we will not multiply it by the SVM coefficients of the whole body, but we will multiply it with the SVM coefficient of the, for example, the head, which is this part, and then with the right part, and with then the left part, and then this part, and then the legs. And then we will add them together. With this approach, we will get a better resolution, or sorry, a better accuracy. So we will get a better accuracy here, because you have like not like HOG plus SVM, but you have taken like the body, and then you have divided the body itself to parts, so you are like know exactly that this is a human body. So now, what is the advantage of using DPF on HOG plus SVM? So one of the advantages is, like, if you have a human, like this is a person, and then we have another person like behind him, then the model will get confused, because these 2 legs, like, they are beside each other, and we can detect it by our eyes, but unfortunately the model can't detect it, and it will get confused. So we are solving it using DPF, as DPF is having, like, I have a human here, and then I have each part, like this part, and then this part and this part. So it will detect, like, because it's dividing and detecting part by part, it will gain efficiency. That's why we are using DPF. Now, to detect human body in an image or a video, second step is to detect or to estimate pose. And to be honest, there are some methods that are used to estimate poses. Like 2 of these methods, which are like the famous ones, are deep pose and dual source deep neural networks. So let's discuss deep pose. So deep pose, to be honest, is one of the first papers to apply deep learning on human pose estimation. And in this, what is interesting in this paper, that they have proved that CNN can be used for localization after it was only used for classification. So deep pose has two main stages. The initial stage, which is used to detect joints on the image, and the second stage, which they have called stage S, which crops the image where the joint had detected, and it uses cascaded regressors to refine the prediction. So let's see here, let's have an example. So if you have an image, then you will apply to it like the deep neural networks based regressor, which is the CNN, and then we will detect that there is a joint here, but this is too far, so we will refine it, so using the second stage, which is called stage S. So we will crop the image in this part and then feed it again to a regressor to refine it to a deep neural network. So here we have like another output and then crop it and so on. In this example, it explains what I have said. Like we have an initial stage, and this stage 2 and stage 3 are the stage S. So in the initial stage, here you can see the output or the pose estimation is not that accurate. But again, when we refine it, it will enhance or it will be approved. And then in stage 3, finally, it's like totally detect the pose estimation, like it's enhanced and it's efficient. The second approach is dual source deep neural networks. Here they have tried to use two patches, apart patches, which is the part of the body, and the body patches, which is the full body, and it's used to get more reliable pose estimation. And they have tried it on two different data sets, and it to give them, to be honest, a really good results and a better precision in some body parts, and it produces superior performance against several methods. As an example, we have this image. So they have divided it to two patches. So the first patch you have the full body, and the second patch you have the foot only, and then you will like feed it to a neural network, a deep neural network, these two parts, and then it will detect the pose of the right ankle, the x-axis of the right ankle, and the y-axis of the right ankle, which is here. So now we have explained the human detection, like the body in the human body detection in the image or the video. Second thing, we have explained also the pose estimation. The last thing, how can we recognize emotions? The last step. So emotion can be recognized using several methods, but we will discuss like only two methods here, which is C4.5 and BiasNet. C4.5 is a type of decision tree, and its advantage is that it works with both continuous and discrete data, as well it can handle incomplete data well. The second one is BiasNet, which is a probabilistic graphical model, and it represents a set of variables and their conditional dependencies. One example, for example, we have a given symptoms of diseases, and the network can compute the probability of presence of various diseases. One of its advantages also is that it can be used for small data sets. So one of the most interesting papers, which has made some experiments on recognizing emotions, is affect recognition from face and body, early fusion with late fusion. In this paper, they have used multimodal, mainly facial and upper body gesture, to recognize emotions. To be honest, I've chosen this paper because, like, in facial only, like in facial expression, it gives some results, but when you add the upper body gesture, it enhanced the accuracy, which we will see later. And yeah, I would like to emphasize about the importance of using the body gestures as well as the facial expressions to detect emotions. So they began with feature extraction. So in this experiment, they have depended on the change of the body actions and the change in the face experience. Like, let's make it easy. Like from neutral, like a frame with neutral expression to a frame with an emotion expression. Like you have like a neutral pose if you are not doing like just standing, and then you began to be happy or excited, you will raise your hand up. So they have tried to calculate the displacement between the first frame, which is the neutral one, the neutral pose, and the second frame, which is the happy pose. There is a change, so they are trying to calculate the displacement. And in this experiment they have used two models in emotion recognition. They have used monomodal emotion recognition and bimodal emotion recognition, so that they would like to compare between them. So in this one, so first step, they have extracted the face expressions, the face input, and they have extracted the features from it. And then you have the upper body. They have extracted the features of the upper body. And then they have used two methods, a feature level fusion method and a decision level fusion method, in order also to detect which one is better to recognize emotions. So the first one, they have these feature vectors, the facial feature vectors, and they have applied it to a model, the emotion model, with the feature vectors of the body. The second one, they have detected the emotion separately for the feature for the facial feature vector, and for the body feature vectors also. They have extracted the emotion, or they have recognized the emotion. Then they have tried to see which one is better, and then they had a decision. So they have used a classification technique in the monomodal, as I've explained there. And for the face one, they have created 8 motion classes, which is anger, disgust, and so on. But for the upper body, they have created 6 emotion classes, and they have combined like anger with disgust, anger with fear, anger with happiness, and so on. And they are claiming that they have combined it so that the upper body modality is an auxiliary mode, but the face modality is the primary mode. And then they have got, like, after applying the C4.5 classifier on faces, they got accuracy with 78%. And for the body alone, they get, using BiasNet, they got 90% accuracy to classify emotions. Then they have used the bimodal emotion recognition, the feature level fusion, and the decision level fusion, which is combined here, and here the emotion are alone, as I have said in the previous slides. And they have found that, like, in the decision level fusion, the accuracy is around, as you can see, 84%, and here it's around 96% in the future level fusion. And from this we can conclude that when we used monomodal emotion recognition with only face expression, we got an accuracy of 78%. But after adding emotion recognition from upper body too, the accuracy has increased to 96%, which we have here. So a brief example for an application is violence detection. To be honest, it's one of the interesting fields that emotion recognition can be used in. So this paper, Violence Detection in Video Using Computer Vision Techniques, has discussed violence detection, as they have analyzed hockey fights dataset. So they have used bag of words approach which is becoming popular for image and videos understanding. They have extracted histograms from these techniques, and then they have fed it to an SVM, support vector machines, to classify if this is a violence or it's not a violence. And for 1000 clip in hockey dataset, this approach got an accuracy around 90%. And here comes the end of my presentation. I'm waiting for your feedbacks. Thank you so much.